And the second problem we want to look at is somewhat related, and it's called the flatness problem. And what it says is, how come the universe is flat? Because again, our old friend, the cosmic microwave background, tells us that the total density parameter of the universe at the current time, we'll call that omega 0, is 1.001 plus or minus 0.002. The universe is flat. There's no special reason to believe the universe should be flat. There's nothing in any fundamental physics that says, at birth, the universe must have the critical density. It could be way below, it could be way above, it could be somewhere in the middle. Why is it that it has that critical density? And the first thing you note, and when I was an undergraduate student this was more plausible than it is today, is that this number is not exactly the critical density, so maybe it's just a little bit off the critical density. But even now, you're talking of it being within a few parts in 1,000 of the critical density. You know, when I was a student, omega was constrained to be about 1.2 plus or minus 0.2, so you could have quite a lot of wiggle room. Now, there's very little wiggle room because you're already knowing that you're within 1 part in 1,000 of the critical density. And then it actually gets worse than that, because let's imagine not just why that is so close, but let's look at the evolution of the density, or the change in the critical density with time. In particular, of variations from critical density with time. And we've already noticed that as long as you don't change what your energy sources are, you can't cross that line. You can't be negatively curved and then become flat and then become positively curved. You're kind of dialed in for that permanently. But that doesn't mean that you can't become more negatively curved or more positively curved. So let's just look at what that's going to be. And to do that, we can go back to our old friend, the Friedmann equation. And that says the following. It says, if you can all remember it now, it's been a few lectures since we've seen it, so see if you can remember it off the top of your head as I write it. Pi g e over 3c squared minus kc squared over r naught squared a squared equals h squared. So that's what the Friedmann equation looks like. I'll just start off by dividing this by h squared. And I just end up with 1 equals 8 pi g over 3c squared h squared e minus kc squared over r naught squared a squared h squared. And then I notice, if I look at the Friedmann equation up here for a flat universe, so if I look at this equation and I strike that out because I'm interested in the flat universe, then 8 pi g over 3c squared is just 1 over the critical density. So what I can therefore write is that 1 equals e over ec minus kc squared over r naught squared a squared h squared, or alternatively 1 minus omega, because this thing is just equal to omega by definition, as a function of time, equals minus kc squared over r naught squared a squared h squared. And what you might immediately think is, well, here we are, I have, as a gets bigger, my deviations might get smaller. But of course, h sits in here as well. So I have to worry about what my scale factor is doing, but also what my Hubble parameter is doing. So I only need to do two things to get this back into a shape which makes sense. So the first thing I'm going to do, I'm going to evaluate this at the current time, at a naught equals 1. And then I can just write that k over r naught squared is equal to h naught squared over c squared into omega naught minus 1. And I can substitute that back into the Friedmann equation. which is all the way up here. I'll substitute that back in here, which gives me that h squared equals 8 pi g e over 3c squared minus h naught squared over a squared omega naught minus 1. And if I then divide by h naught squared, then I get h squared over h naught squared is equal to e over EC0, because again, when I divide this by h naught squared, this bit here, 8 pi g over 3c squared h naught squared, is equal to the critical density now, plus 1 minus omega naught over a squared. And then if I split this up into matter, radiation, lambda, for example, I get that h squared over h naught squared is omega m naught over a cubed plus omega r naught over a to the 4 plus omega lambda plus 1 minus omega naught over a squared. And we have got that, you'll see that also in some earlier PDF notes, I think from lecture 3. And this actually is an interesting way to actually solve the Friedmann equation in multiple different components. I actually don't need to do that today. If I'm looking backwards in time, I am only caring about matter and radiation. Then I can write this as h squared over h naught squared equals omega m naught over a cubed plus omega r naught over a to the 4. Okay. So let's just box this, because I'm going to come back to this in a minute. I don't know quite why we've got a fill style here. I want no fill at all. Let's go to fill. Yeah, there we go. That's better. Right. So we can box that, and I should probably also have boxed this equation up here. And again, if I evaluate that at the current time without doing the rejigging I did when I did this bit here, then I can write very simply 1 minus omega 0 equals minus kc squared over r naught squared h naught squared, because remember a0 is 1. And I also, of course, have that more generally, that 1 minus omega is equal to minus kc squared over r naught squared h squared a squared. And then I can divide those two together. And I get that 1 minus omega, I'm not doing very well with my omegas today either, omega as a function of t over 1 minus omega 0 is equal to h naught squared over h of t squared a of t squared. And then I can just substitute in for h squared over h naught squared, so this bit here, from my boxed equation up here, and I get that 1 minus omega t is equal to 1 minus omega naught a squared over omega r0 plus a omega m0. And so this term, the 1 minus omega naught, we know is small. but we don't know that it is 0. If it is 0, of course, it's flat forever. A flat universe remains flat at all times. But then these numbers here, this is very small. Right, omega r0 is very small, and omega m0 is 0.27 or something like that. So this looks like it's going to scale. 1 minus omega is roughly going to scale as A in the matter-dominated era, and it's going to scale as A squared in the radiation-dominated era. So if we look at the point, when A is 10 to the minus 4, i.e. around the time of the CMB, it's a bit earlier than the CMB, then, 1 minus omega is now about 10 to the minus 6. If I go to the Planck time, that's perhaps the time you might expect all these things to get set, 10 to the minus 44 seconds. 1 minus omega is about 10 to the minus 60. So in other words, in order to get the universe to be looking fairly flat today, it had to start exceptionally flat. So the universe today looks like it's flat to 1 part in 1,000, but that means that early on in the universe, if we just run back with matter and radiation, it was flat to 1 part in 10 to the 60. That is extraordinary fine-tuning. So either, probably, it really was flat, or something else is going on here that we still need to get a good understanding of. And that is the flatness problem, which is one of the other key problems that we want to consider.